Hello, my name is Eric Mears, and this is a worked out solution to the book problem 3.81. The question given here is the cantilever bar in the figure down here is made from ductile material and is statically loaded with Fx being 0, Fy being 175 pounds force, Fz is equal to 100 pounds force, and the question is to analyze the stress situation in rod AB, shown right here, by obtaining the following information. So the information that it is looking for, listed under what is required for this problem, is to determine the precise location of the critical stress element, sketch the critical stress element, and determine magnitudes and direction for all stresses acting on it, and C, for the critical stress element, determine the principal stresses and the maximum shear stress. First off, in the procedure, nicely listing all the given information from the problem, which was the Fx, the Fy, and the Fz. And then here is the figure that is shown for the problem. Okay, so now to solve this problem, we are looking for the precise location of the critical stress element, and that's going to be somewhere on this plane right here at A. In order to find that, we're going to start with finding the momentums from the forces given, and the moment of x is going to be 0 due to the f of x is equal to 0. My is going to be Fz times the distance away that the force is, which is 8 inches. And then plugging in the value of Fz, 100 pound force, 8 inches, and Y is going to end up being a negative 800 pound force times inch. And lastly, we have Mz is equal to Fy times 8 inch, which is going to end up plugging those values in. Multiplying those two values, we get an Mz of 1,400 pound force times inches. And then to find the moment of the total reaction, we're going to take the square root of both of those momentum values squared. And then Mr is going to equal 1,612.45 pound force inches. Okay. From there, so we have one part that we need, but we also need which point on that plane that's going to be at. So in order to find that, we're going to use the equation theta is equal to tangent, or the inverse tangent of My over Mz. So this is the magnitude. And the direction here, if we plug in My and Mz there, it's going to equal 29.74 degrees. That is going to be the direction of that force there. And then with that, we can also see that the torque at point A, using that torque of A is equal to negative 175 pound force times the 5 inches away, given right here, of the torque on A is going to be negative 875 pound-force times inches. Okay. And that is all under part A. I'm going to move this up. Get a new sheet of paper for this part. And we're going to start on part B. Part B is asking to sketch the critical stress element and determine magnitudes and directions for all stresses acting on it. So for us to do this, we're looking for the stresses at point A. To start off, we'll look at the bending stress. And with the bending stress, we find the equation to be 32 times the reacting moment, divided by pi d cubed. And then plugging in those numbers, we have 32 times 162.45, where pi and the diameter is 1 for that bar A. Then we can find that the bending stress is 16,424.28 psi, which is also equal to 16.42 ksi. So there's one. Another stress that's going to be acting there is the torsional shear stress. That's going to be at the cross section of A. And that equation is going to be negative 16 t over pi d cubed. And then this is where the torque at A comes into play. That torque is negative 875 pound-force per inch. And this is all divided by pi 1 to the cube. Plugging in those to our calculator, we get the value to be 4,456.34 psi, which is also equal to 4.4, let's go 56 ksi. The last kind of stress that we have to look at is the transverse shear stress. The equation for that is given to be 4v over 3a, which we can plug those values in. For v, it's going to be 175, and then you plug in 3, and then the equation for area is going to be pi over 4, and we're going to multiply it by that 1, the diameter of 1 squared. And the transverse shear stress ends up being 297.1, and that's in psi. Okay, and then from these numbers here that we have gotten, we can show combining these two values that the stress through that cross section we've got the bending and torsional coming together. We can place that right here. And that's in KSI. And then the torsional shear stress it's also in KSI. So we get this figure for that cross-sectional area. And then if we look at the bending, if you look at the cross-section for A, the forces are going to come through these points here and be pushing at that angle theta. It's going to look like that, and that's bending due to the moment of Z and the moment of Y. And then also from this information, we can show that, and also given from part A, at that theta, that this is the cross-sectional area. Okay, so then we get these three figures, which answers the question to sketch the critical stresses elements and determine the magnitudes and directions for all the stresses acting on it. And then so now we can go to part C. And part C says for the critical stress element, determine the principal stresses and the maximum shear stress. All right. So determining the principal stresses. First, we're going to find the principal stresses, which is the equation for the principal stresses is that shear in the x direction. This is the square root value over 2 squared. And if we're going to plug in those values, we find it to be there's 16.42, remembering that that is in KSI. And then we saw earlier, this value is 4.456 squared. And then if we do, for theta 1, we're going to be using the addition, and plugging those into our calculator, we get 17.6 kpsi, and that is the maximum principal stress. And then the second one is using the subtraction, which is going to be negative 1.13 KSI. Same thing here, KSI, and that's actually going to be the minimum principal stress. And then now we need to find the maximum shear stress. And the maximum shear stress is given by the equation Tmax. Using that squared plus, as you notice, the max shear stress is the same as this part of the principal stress. And then plugging in these values here the exact same way. That Tmax, that max shear stress, is going to be 9.34 KSI. That is the max shear stress. Looking back on all this, to recap, writing down the problem, writing down what is required, and then from there, making sure we have the givens listed carefully, as well as the figure shown, and then just making sure to use the correct equations to go through the process, and making sure that especially the stress is at A, doing the bending stress, torsional stress, transverse stress. And that is all. Hope you have a great day.